structured solution with powder diffraction. After that, we will head off to the computer room for the hands-on data analysis. Thank you, Joel.
All right. Can everybody hear me okay? Hopefully you guys had a good lunch. So we talked a little this morning about how you do a Rietveld refinement, the elements that are important for doing a Rietveld refinement. And we mentioned that a Rietveld refinement is a refinement method. It's not a structure solution method. So the question is, what do you do when you don't have a structural model for your material? And that's going to be the focus of this talk. So in order to perform Rietveld refinement, we know we have to have a crystal structure. It's worth noting, if you have a single crystal of your material, it's definitely worth making use of it. Single crystal XRD is the most common and generally the easiest route to a new crystal structure. So if you can synthesize a single crystal, or if you have a large single crystal, definitely make use of it. It's the easiest way to do it. But a lot of technological materials, you just won't be able to solve, or you won't be able to generate a large enough single crystal to actually solve the structure. So that can be a major problem.
So what is large enough?
What is large enough?
Yes.
Probably depends what kind of diffractometer you have. With the synchrotron, sometimes you can go down to 20 microns and even smaller, depending on the beamline. So you can get by with a very small single crystal, potentially. I think in the lab, I'm not a single crystal expert, but you're talking more high tens of microns. So you're 50 microns, probably larger is more ideal to get strong enough scattering. But, pardon? Well, like I said, probably you can get down to 20 microns and even smaller with certain synchrotron beamlines. So really, it depends a bit on the beamline, how small you could actually get it.
Bob mentioned that in solution you could go even smaller. Did you mention that this morning that you could get away with 5 micron size crystals in solution? For single crystal? Maybe.
I guess the only thing is that those folks doing single crystal diffraction, one crystal at a time at those extreme light sources. Those crystals are on the order of about 2 microns. But it's sort of, I like to kid them saying that it's powder diffraction one crystal at a time. But they do manage to get single crystal data from each one of these single crystals. And eventually wind up accumulating enough spots on their detectors to get a single crystal data set from a whole string of 1 micron crystals. But that's really the exception. Smallest I've heard in the synchrotron is something like 10 micron. But that's pretty specialized material, specialized circuits. But more typically, if something says it's 50 microns or 100 microns, that's more typical single crystal size. Yeah, not too big anyway, because bigger than half a millimeter, the single crystal winds up longer than the side of the beam partially, and you get screwed up intensity. So, yeah.
Yeah, for lab diameter, 100 micron of the medium size.
Okay. Right. Yeah. So, and solving structures with powder diffraction data, it's challenging, but it's actually quite rewarding, especially if you like doing puzzles. It's a really interesting undertaking, and it's kind of addictive. So if you try it, you may not be able to stop.
Brian Tovey's line about this is that trying to solve a crystal structure from powder diffraction data, the structure actually has a chance of not being solved. So much more of a sport than single crystallography, which is just trying to find the atoms.
So I showed this diagram in this morning's presentation, And part of what makes PXRD structure solutions so challenging is because of that inherent loss of information that you get doing a powder diffraction pattern. PXRD structures are often underdetermined relative to single crystal structure determination. So I reminded you this morning, with a single crystal, what you're doing is you're putting the crystal in the beam and then rotating it in very small angular increments to get a whole series of different patterns. So you get every individual Bragg intensity with very accurately and with a lot of redundancy. But with powder diffraction, you're basically condensing all of that information into one image. You're merging it onto one image. So peak overlap becomes a much, much bigger problem. And ultimately, what this generally means for structure solution is you typically have to have much more initial information. You need to know more about your material than you do with a single crystal. And you often have to use detailed chemical restraints in either the solution or both the solution and refinement processes. We'll talk a little bit about that. It's also very helpful, if you can, to validate the structure solution with other techniques. DFT, or density functional theory, is a very good way to do this. So there's a few things you want to try to do before solving a crystal structure. First, you want to carefully look in the literature and see if somebody else has already solved your problem for you. And you'd be surprised how often this happens. You think you can't find a structure for something, but somebody out there has actually done it already. Doing phase identification with the powder diffraction file on your data can be a good way to screen and see if there's anything there, particularly for inorganics. For organics, using formula and unit cell searches in the Cambridge Structural Database can be very, very helpful to see if anyone's observed the same thing. You always want to make sure you have the best sample possible, particularly with respect to purity. You can save a lot of time in the long run by getting a very pure, high-quality sample than trying to deal with a sample with impurities, and it just creates a great degree of uncertainty. You always want to have a hypothetical chemical formula, and ideally you want to have confirmed this, if you can, with elemental analysis, if possible. Often you'll have a very good idea of what you've synthesized, but even really good chemists occasionally encounter surprises in their synthesis that they didn't expect. And you want to make sure you have the right kind of diffraction data that's appropriate for the task at hand. And often for really complex problems, this means that you want synchrotron or synchrotron and neutron data. So here's just a refresher on the features we need to solve a crystal structure. Basically, our peak positions are allowing us to determine what crystal system and lattice parameters we have for our unit cell. And the systematic absences allow us to determine the possible space groups that describe the symmetry within the unit cell. Our peak intensities are what are telling us where the atoms are located. So we use these to figure out where the atoms are placed within our unit cell. These steps go in order, so before you can solve the structure, you have to figure out the unit cell and the space group. If you get that part wrong, again, you can spend an awful lot of time chasing down wrong answers. Generally, the thinner the peak width in your pattern, the easier it is to accurately determine both the positions and the intensities. So this is one reason why synchrotron is very useful for structure solution, getting high resolution data with as minimal peak overlap as possible. So this is what's known as the structure solution maze in powder diffraction. So to get through the maze to the final structure, there are a bunch of steps that you have to complete in order, and there are decision points where you make choices which can be the difference between success and failure as you're doing this. And as we go through all these steps, I'll highlight some of the software packages I'm using. Generally, I'll keep the software packages in parentheses, and I'll have bolded the ones that I'm most familiar with, or the ones that I use the most. It doesn't make them the best choice, it makes them the ones that I've used. So these are the main steps in structure solution. We'll be going through all of them in a little more detail. I already emphasized, you really want to get data that's sufficient for your task. Success in PXRD crystal structure solution is not guaranteed. So you want to give yourself every advantage you can to get to the right answer. You have to index the data to determine your unit cell and your space group. This often blends into the next step, because using structureless refinements like Lebail and Pawley refinements, which Bob discussed this morning, they can be very important for testing your unit cell and space group combinations to make sure that you've got the optimal one. When you think you have the optimal cell and a good Lebail or Pawley refinement, then you need to choose a method of structure solution. And often this entails trying more than one method until you obtain a basic structure that explains the pattern well and it looks chemically plausible as well. And once you have a basic structure, you test it with Rietveld refinement. And often you'll have to use what are called difference Fourier maps to locate missing atoms and complete your structure. And finally, if you get a really good looking Rietveld refinement that looks chemically sensible in terms of the model, it's always good to confirm or to try and validate that structure with other experimental methods or with DFT if possible. So what types of data should you use? For many moderately complex samples, LabXRD is suitable. It's generally preferable to use monochromatic radiation if possible, but you don't even have to use monochromatic radiation. You can do it with doublets. For complex, really large unit cells with low symmetry, synchrotron data is often preferable, especially for the unit cell indexing, where you can minimize the peak overlap, and that can be critical for actually getting the correct unit cell. If your problem is complex, often you're going to want to use both X-rays and neutrons because they tend to have different but complementary scattering factors. This is particularly important when you have really light atoms in the presence of really heavy atoms because the neutrons will often see the light atoms better than the X-rays will. So if you're working on lithium-ion batteries with heavy metals as part of the structure, often what you're going to need is synchrotron and neutron diffraction. And we won't be discussing magnetic structures here, but if magnetic structure is part of your interest, you really have to use neutrons. It's very good for looking at actual magnetic structure. So once you've got your data, the next step is to figure out the correct unit cell and the space group. Ab initio indexing is an interesting step because depending on the sample purity, on the data quality, and the complexity of the unit cell, it can be a really, really easy step, or it can be a very challenging step. There's lots of different indexing programs, and they use different methodologies. I often start with a program called DickVol because it uses a very comprehensive, exhaustive strategy. This makes it really good for finding cells with monoclinic and higher symmetry. For triclinic cases, this exhaustive strategy makes DickVol a very time-consuming option. So sometimes if you suspect you've got a triclinic cell, you're better off starting with a program like Traor, which uses a much faster strategy to actually find the unit cell. And I can't overemphasize this. Bob talked about it a bit this morning. Indexing is always easier with a pure sample. Many indexing programs can tolerate a few impurity reflections, but you're always better working with a pure sample if possible. And if you know a peak is due to an impurity, you want to exclude that from the indexing. So typically you use the first 20 or so diffraction peaks from your diffraction pattern for the indexing portion. Some programs like Ito actually work better using more like 35 reflections. So it depends a little bit on the program you're using, but 20 is typical. Also, sometimes you'll run into problems where you've got a unit cell with a very, very long axis and a second axis that's very, very short. Sometimes in those cases, you want to use more lines as well because it's very hard to pin down what the short axis actually is. There are two figures of merit that are typically used for evaluating your indexing and explaining how well that unit cell actually explains your data. The first is the de Wolf figure of merit, which is formally defined for 20 diffraction peaks, but it can be generalized to any number of diffraction peaks. And generally, if you can index something, the first 20 lines of a pattern with an M20 value of 10 or greater, your indexing is substantially correct. And by substantially, what I mean is you either have the correct cell or you probably have something that's quite closely linked. There are exceptions to this rule, but in general, that's a good rule of thumb. The second indexing figure of merit is the Smith-Snyder figure of merit, and it's formally defined for an arbitrary number of index peaks. And for both of these figures of merit, essentially, the higher the value you get, the better a match you've got. So since they use different strategies, it's very helpful comparing indexing results that are obtained with more than one program. I mentioned I frequently use Diffraction, but even if I don't initially find a unit cell using Diffraction, I often try and reproduce the result in that program after the fact to see if I can come up with the same unit cell. And there are software suites like FullProf and Expo, which actually provide access to more than one program. So it's very easy to compare results because you can do your basic data reduction and peak selection once, and then you can run multiple programs and see what kind of results you get. And once you've determined what you believe is the correct unit cell, then there are programs that can specifically determine the possible space group by looking at systematic absences in the observed reflections. I often use a standalone program called c.l.s for this, but Expo and GSAS2 also can do this as well. And it's always really important to remember that the size of your unit cell should be appropriate for a reasonable number of formula units, which depend on the symmetry, or specifically the general multiplicity of the space group. So your unit cell contents need to make sense with the unit cell you choose. To give you a little example here. So for organic compounds, you can estimate the number of atoms in the unit cell by dividing the unit cell volume by 17 or 18 angstroms per non-hydrogen atom. Some software packages also provide calculators or estimates that can be used to compare the volume with the formula and the number of formula units, or Z. I have a little calculator I talked about this morning called MAC, which I've shown on the right here, and it can estimate your Z value from the formula and the volume for different types of compounds, and it can also calculate the mu-R value. So right here, basically you can put in your formula and you can put in a cell, and then you can calculate how many formula units you should have. And then you can also put in your experimental conditions, including your capillary size, to determine your PXRD mu-R. So in this case, what we're looking at hydroxyapatite, calcium hydroxyapatite, and it's estimating that there should be 1.8 formula units. That's pretty close to 2. So what I typically do is change this to 2, which is the correct value, and then you can calculate your PXRD mu-R. Once you have a tentative unit cell and a space group with a volume that's compatible with the formula and the expected number of unit cell contents, the next step is to fit the data with a Lebail or a Pawley refinement and to see how well that unit cell actually describes your pattern. And often this step blends into the previous step. So what you'll do is you'll get a few different unit cells that look like they could be possibilities, and you try Lebail or Pawley refinements, and you compare and you see which one you believe is actually the very best fit. So the Lebail and Pawley methods were devised specifically to facilitate this full pattern refinement without the need for a crystal structure. So they do require a unit cell, but you don't necessarily even have to know the correct space group. You can often, for an unknown structure, you can test a few different space groups and see which space group option or which setting of that space group actually works the best. So both of these methods fit the peak intensities to best fit the experimental data. So you can use them to extract an estimate of the peak intensities, which is often an important precursor step to doing your structure solution. And similar to Rietveld refinement, these methods work best when you know your instrument resolution. So you know the geometry very well and you've got instrument parameters, but you can also use them to get an estimate of the profile parameters for your instrument as well. The methods are similar, but they have some differences, which Bob pointed out this morning. The Pawley method internally treats every Bragg reflection intensity as a least square parameter. So that makes it kind of computationally intensive because every single peak has got a refinable parameter associated with it. The Lebail method uses something called an iterative intensity partitioning method to obtain the intensities. So mathematically, the Lebail method is actually more similar to the Rietveld method than the Pawley method. And traditionally, that means it's probably been incorporated into more different software programs than the Pawley method has. Personally, I've almost always used the Lebail method based on the software packages that I've used the most. But both methods can be good ways of doing it. And the contrast in the way they work can actually sometimes be helpful as well for structure solution. So, oh, and Bob has got a comment here.
There's something else that's different about the Lebail method versus Pawley method. You can use that too. The Lebail method is for one phase in one data set. Okay? The Pawley method actually allows you to fit one set of structure factors across a range of pattern patterns. So that you can have one set of structure factors for, say, 3 or 4 outer patterns collected at slightly different temperatures where the lines have shifted relative to each other. Maybe get better structure factors because you solved the overlap problem. It's a thought.
Yeah.
But that the Pawley method of SITZ2 allows you to do that.
So since the Lebail and Pawley methods don't require structures, they're actually very useful for comparing to the Rietveld method because they give you an estimate of the best fit you can obtain with the Rietveld refinement. Because there's no constraints on the intensities, you should always get a better fit with your Rietveld or your Pawley refinement than you, or sorry, with your Lebail or Pawley refinement than you do with your Rietveld. So you can see here for this example, the difference curve is a little bit flatter for the Lebail refinement than the Rietveld refinement. And the reduced chi-squared value is still well within a factor of 2. It's lower for Lebail, but it's not too much lower, the reduced chi-squared. There's no hard and fast rule, but if your reduced chi-squared for your Rietveld refinement is more than twice as large as for the Lebail refinement, you probably want to take a look at your Rietveld refinement and see if you aren't missing something or there isn't something that can be improved in your refinement. In this specific case, this structure was confirmed with comparison to the density functional theory, optimized structure, so we can be reasonably confident that the crystal structure is correct. And I'm going to talk a little bit more about DFT towards the end here. So once you have a unit cell and a space group combination that agrees with your expected formula, and you've got a decent Lebail or Pawley refinement, the next step is to actually attempt to solve the basic structure. And this occupies the entire top half of our maze here. There's generally 2 routes you can use to solve the structure. You can use what are called reciprocal space methods, or you can use what are called direct space methods. And we'll take a look at both of these types of methods. Often you won't obtain the exact structure in the initial structure solution, but something that's reasonably close that you need to do some refinement or perhaps make some manual modifications to. And this is particularly true for inorganic crystal structures. So there are different techniques and approaches that are associated with both reciprocal and direct space methods. I've listed a few of them here, including some of the common software. Reciprocal space methods generally use intensities that are extracted from the PXRD pattern during the Lebail or the Pawley refinement. In this way, they're more similar to classical single crystal XRD structure solution methods. They tend to require less upfront chemical information about the unit cell contents, but they generally require very high quality data in order to be successful. Direct space methods require more upfront chemical information. What you actually have to do is you have to build a fragment or fragments that are plausible for your model. And then what happens is the solution method uses global optimization strategies to manipulate those fragments or the model and move them around in the unit cell to help best explain the powder pattern. So for reciprocal space methods, they're very similar to single crystal structure solution methods, where the extracted intensities or individual Bragg reflection peaks are used to solve the crystallographic phase problem. In order for these methods to work, you generally have to have accurate intensities to find enough accurate intensities to find the atoms in the structure. And accurate intensities typically have to go down to nearly atomic resolution or close to 1 angstrom. So you need a lot of high quality data. So a synchrotron can be essential for getting thin enough peaks to actually solve a structure with reciprocal space methods. And these methods tend to work better with smaller, higher symmetry structures, and again, with really high quality data. One nice advantage, though, is they typically require less chemical information to get a rough solution. So although more information is generally still helpful, you can get away in the initial stages with less information. Oops, did I? Okay, so now what we're going to try is a straightforward structure solution using the Expo software package, just to give you a demonstration of how this is done. And we're going to look here at cytosine, which is a purine base that forms one of the 4 building blocks for DNA. So I'm just going to switch computers here for a second. Good. Come back. All right. So I'm going to use Expo here. And all we're going to do to start with is we're going to import our diffraction pattern into Expo. I've obviously got it buried down here, so it's very hard to find. And it's going to ask us for the radiation wavelength. And our wavelength for this particular pattern is 0.68908. And it's monochromatic because it's synchrotron radiation. So here's our powder pattern. So the first step is picking our peaks. So I'm going to go to Pattern and Peaks, and I'm going to choose these peak search conditions. And I'm only going to use the data I need for the indexing here. So I'm going to set this minimum 2 theta to 5, just to make sure we don't get spurious peaks at low angle that aren't really there. And I'm going to end the data at about 20 degrees. I'm going to lower this intensity threshold for finding peaks to find as many as I can just with the automated routine here. Go down to about 0.5. I'm going to say OK. Now I'm going to zoom in on our region here to see what peaks are missing. If I go back to Pattern and Peaks, I can add or delete individual peaks in here. So I'm going to choose Add Delete Peaks. And I'm going to add, there's pretty clearly a peak missing right about here. And there's a little one missing right here. And that's looking pretty good. Now we've got more than 20 peaks. So what we can now try and do is to index the pattern. So I'm going to go to Indexing, and I'm going to choose Dickval. And I'm not going to change much here in the defaults. So you'll notice Dickval it automatically picks every crystal symmetry except for triclinic, because triclinic tends to take a long time with Dickval. So we're not going to choose triclinic because it's not triclinic in this case. I'm going to make the peak position error slightly larger. Its default is 0.01 degrees. I'm going to make it 0.02 degrees. This is synchrotron radiation, but it's not particularly high resolution synchrotron. The peaks aren't that thin. So I'm going to choose a slightly larger peak position.
So before you imported the data, is this with background subtracted?
No, this is the native data. Though it subtracted it itself, I think, when it was doing, well, let me see, on the axis. It may have subtracted it when I don't think it did. It'll do a little bit of manipulation here as it does a Lebail refinement, but I just imported the data as is. Well, as is after it was 2D data, so it was integrated. So what it does is it goes through a little routine to find the peak positions. And this is not a big unit cell, so it found some examples really quickly. So if you look here, there's 4 unit cells, but they're all quite closely related. The top one up here, which has the highest M20 of about 58, is orthorhombic. The next 3 cells are modifications on that orthorhombic cell, making it slightly monoclinic. And this is, the orthorhombic cell is the correct cell. We've got the right cell. So it's got the highest M20 figure of merit in this case, so as we might expect. And it's also got the highest symmetry, which is another good sign that we've got the right unit cell. So we're going to choose this top cell, and I'll say OK. Then what we can do is put in the formula. So in this case, this is for cytosine, this is C4H5N3O. And you'll notice I put it in parentheses, that formula. So it's saying 1 formula unit, it's estimating it should occupy a volume of about 127 cubic angstroms. The volume of our cell is about 4 times as large as that. That's another good sign. A lot of orthorhombic structures are going to have 4 or 8 molecules in the unit cell because of the multiplicity that's associated with an orthorhombic cell. So if I stick a 4 on the end of this, you'll notice now I'm getting a cell contents of just over 500 angstroms, and it's pretty close to the volume of the unit cell. Sorry, did you have a question?
Would it consider also the intensity when indexing things, or it's only the peak position?
For indexing, it's just the peak positions. When it does the structure solution here, it's all about the intensities. So I'm going to suggest that there should be 4 formula units here. We're going to say OK. And I have to press a button here. What it's going to do is it's going to run a Lebail refinement to try and extract the intensities. You'll notice there's some extra peak positions down here because we haven't defined a space group, but they're not real, and it's finding very, very little down there. I'm going to say next again. So now it's suggesting what it thinks are the possible space groups. This top choice has the highest figure of merit, and in this case, this is the correct choice. This can be tricky sometimes. Sometimes you have to look at a few different space group options and try and figure out for yourself what do you believe is the correct choice. A nice sign with this one is for orthorhombic, P212121 is a very, very common space group, particularly for organic structures. So that's a very good sign that we probably have the correct space group here. So I'm going to say OK. And it's going to do another Lebail refinement having used that space group. And you'll notice now some of those low angle reflections have actually disappeared because they're not present in the space group. And it uses this to uses that Lebail to extract the peak intensities. And then it's using what's called direct methods. And this actually happened really fast. And you'll notice we've got what looks like a cytosine molecule. All right, so a couple cautions. It never, ever, ever actually goes this way. I chose this example very carefully. I picked something with fairly high symmetry, a small unit cell, reasonable quality data, and it came out in a couple minutes. It never happens this way. I use Expo. I like Expo because it is fast, but typically, in my experience, when you use Expo with direct methods, it's going to be successful 10 or maybe 20% of the time. More often, you're going to have to move on to a different strategy. So the second thing is, if we look at this, it's basically got the atom, it's got our molecule in the right setup, right? But if we look back at the actual molecule, I'm going to switch back to the main PC for a sec, if it'll let me. The nitrogens aren't in the same position. So one atom is at least swapped. This third nitrogen was right here in our solve method. So having chemical information is really important because you're going to get, it basically found the right basic structure, but there wasn't an atom swapped. And if you didn't know that from other methods or chemical intuition, various things, if you didn't have that information, you wouldn't know. So, but it's providing a basic building block now to do a Rietveld refinement. The other thing here is you don't have the hydrogen positions. So, all right. So that's reciprocal space methods. The second type of methods are direct space structure solution methods. And they were designed to use the entire powder diffraction pattern rather than extracting the integrated intensities. And they were designed from the beginning with powder diffraction data in mind. So these methods use algorithms which move model fragments around in the unit cell. And they compare the results that are from a calculated pattern to the observed pattern. And when the agreement improves, the new model is saved. And occasionally, every so often, when the model doesn't improve due to a move, it's still saved. And what this does is it allows you to avoid false minima or local minima to get to the final correct crystal structure. Because if you only saved things where they improve, you could end up in false minima. There aren't the correct crystal structure. So for these direct space methods, you have to create an appropriate starting model in order to use them. You have to have some chemical information. For inorganics, typically what you need is the elemental composition and the expected coordination polyhedra that you believe will be present in the structure. For organics, you typically have to have reasonable starting models for all the molecules that are present in the structure. And this can require model building if you're looking at a molecule that hasn't been observed in a crystal structure before. A big advantage of these direct space methods is that they can be successful with lower quality data and with less data content than reciprocal space methods. So you can get by more easily with lab data and with poorer resolution. So let's look at a direct space structure solution, and this is using parallel tempering with a program called FOX using laboratory data. This is a compound I mentioned in my first presentation called trandolapril. It's used to treat hypertension or high blood pressure. And with this powder pattern, we could index it pretty easily with Dickfall to an orthorhombic cell, which had space group actually P212121, the same as the previous example we looked at. It's a very common space group for organic molecules. I couldn't find an example of this crystal structure, or of a crystal structure with a trandolapril molecule in it. So I actually had to build the molecule. So in order to do this, I searched the Cambridge structural database for molecules that described half of the trandolapril molecule. So I basically searched for this geometry separately and searched for this geometry separately. And I came up with a few options for each half of the molecule. I ended up choosing these two Cambridge entries, which are indexed by their 6-letter codes. You can see right here. And then what I did was I just manually removed the atoms that I didn't need from the CIF file, just using a text editor in order to obtain the two halves of the trandolapril molecule, like so. And then what I did was I used a chemical editor called Avogadro. This is freeware. And I basically imported both of these fragments into one Avogadro session. And then I manually manipulated them around to attach them by the nitrogen atoms here and here to create a single molecule that looks something like that. Once you have this trandolapril molecule, you can upload it into FOX in order to perform your structure solution. The easiest way to do this is to convert a CIF file into something called a Fensky-Hall Z matrix. This is very easy to do with a program called OpenBabel. And OpenBabel is a great little free program because it'll allow you to do conversions between dozens of different chemical file formats. So if you use a lot of different software, which powder diffraction people tend to, it's very helpful for getting between different types of formats. And here is a view of the final Rietveld refinement obtained with GSAS. So this data was collected on a lab instrument in transmission geometry, which is a little unusual. So it used a capillary, but it was a lab instrument. And the data quality is really high, but there's not a lot of data. You can see it only goes out to about 40 degrees 2 theta. which is a despacing limit of about 2.2 angstroms. So you don't have a lot of data content. You would have little or no chance of solving this structure with reciprocal space methods using this data. You wouldn't be successful. There is not enough data. But with direct space methods, we can actually solve this crystal structure with this data.
So why would you ever bother to use reciprocal space data? There should be some advantage to it.
It can be very quick. And with high quality data, with the type of data we encounter regularly, like on the low energy wiggler, very, very high resolution data, you can be successful that way. So yeah, the synchrotron definitely makes it easier. There are certain types of problems you only want to really try with synchrotron data because it's just going to be too hard with lab data.
So both the resolution and the intensity matters.
It's mostly the resolution. Yeah, getting rid of peak overlap as much as possible.
And then the reciprocal space methods would be faster.
They can be. You saw that one example that was quite a lot faster. It can be slower as well, but it's typically going to be faster with reciprocal space methods. So, all right. So when you do a refinement like this, you don't have enough information to refine all the atoms freely. Basically, you have to use some restraints on bond distances and angles. A good way to do this is a tool called Mogul, which comes in the Cambridge Structural Database. And with Mogul, essentially what you can do is you can simply upload your structure via a CIF file, and it will identify all the bond distances and angles in that molecule. So what you can do is what's called an all fragment search here. I've highlighted the button with red. And it will produce a list of all the bond angles, bond lengths, torsion angles, and it will also suggest what it thinks are rings within your structure by comparing to similar features observed in compounds that are already in the Cambridge Structural Database. So Mogul will output a list that looks something like this. And you can see there's a tab here each for bonds, angles, torsion angles, and rings. So we're looking at the bonds. And what it'll do is it'll give you mean and median values. It'll tell you the number of different other structures it looks at. And so basically here it's saying over 20,000 structures, it saw a bond that look the same as these bonds in our structure. And basically what you can do is I typically would take the mean and the standard deviation, and you can put these into GSAS to provide constraints, the way Bob was explaining constraints this morning. And you can do the same thing with all of the angles. Typically for the torsion angles, I would not constrain those. Often if you're looking at a new structure, one of the most interesting things can be the actual torsion angle that gets refined and comes from your data. So you sometimes don't want to restrain things like that. And typically in the early stages of a refinement, you put a very high weight on the restraints in order to keep the structure chemically reasonable in the early stages of refinement. And then as you get towards the latter stages, you can lower the actual weight on the constraints so that the data is coming to dominate the refinement after you're very close to the minimum value. So when you get to the end of your refinement and you think you've got a tentative structure that looks pretty good, you want to do a few things to confirm that it should be correct or is likely correct. What you want to make sure you get a really high quality final Rietveld refinement. It should have reasonable statistical metrics, and most importantly, the refinement should look decent. Your visual, and this comes with experience, but looking visually at your refinement, you should be pretty confident that you've got a decent refinement. You want to make sure that the structure is consistent with all the available elemental and chemical data you have. And this can be compositional data. It can also be data like NMR. You want to check the structure to make sure that it looks chemically reasonable. This is another thing that comes with experience. My background is actually in engineering physics rather than chemistry. I joke with my friends that I've basically been an untrained chemist now for about 10 years. But it takes looking at some of these things, particularly if you don't have a chemistry background. You've got to look at them for a while to figure out, okay, what is reasonable? What kind of bonding patterns are reasonable? And finally, if you have the option, you can compare your Rietveld structure to a DFT optimized structure and see how closely they actually compare. And I'm going to talk a little bit more about this right now, or very shortly anyways. So for organic structures, what you can do as well, the same way you can set your constraints or restraints by going through Mogul, you can put your final refined structure through Mogul, and it will tell you if there's any bonds that or angles that look out of place or look unusual. So that's a good final step to check your actual organic structure. For inorganic structures, you can use what's called the bond valence method, and you can see if your bond lengths and your empirically and calculated valences are actually reasonable, because obviously you should know what valences you're expecting based on the geometry. And again, for both types of structures, the ultimate comparison can be to perform a DFT optimization and see how close your DFT and your Rietveld refined structures match. So what is DFT? DFT is a quantum chemical technique that uses the electron density as the basic quantity to calculate the electronic structure and properties of a system. I don't have time to go into the theory, and I probably wouldn't do it justice anyways. So I've put a few really good resources here that you can read if you're interested in looking more. And there's many different programs that you can perform DFT with. At the c.l.s, we have a license to the Crystal software package. So that's what has been used for an example that I'll present here. DFT can be very complementary for powder diffraction work, and more broadly, just for experimental work in general. For many experiments, it's difficult to validate your results. You need some way of critically looking at them to determine if they're correct, and DFT can be an excellent tool for doing this. And DFT can actually provide better details, structural details, than the experiment in certain circumstances. For instance, X-rays do not see hydrogen very well. So DFT is very complementary with your Rietveld refinement to determine accurate hydrogen bonding and hydrogen positions in organics and metal organics, systems like that. And DFT can also potentially give you some insight into properties of your material as well. So particularly for complex organic structures, PXRD and DFT can be very complementary because the PXRD gives you the crystal lattice and the basic packing arrangement, but the DFT can provide you the actual fine details, especially with regards to the hydrogen atoms. Even with synchrotron data, you generally can't refine hydrogen atom positions with powder XRD data. They just don't scatter strongly enough. So DFT helps you get the full picture of your structure. The agreement between the PXRD and the DFT structures can even be used to validate the correctness of the PXRD structure. So these guys, Van de Streek and Newman, they actually looked at over 200 published PXRD crystal structures, and they compared the average RMS displacement between the PXRD and the DFT optimized models. And generally correct crystal structures, PXRD crystal structures, fell below an RMSD of about 0.3 angstroms for the non-hydrogen atoms. Structures with RMS displacements over 0.4 angstroms, in general, the PXRD structure was probably incorrect. And they corrected some of these structures. They actually determined what the correct structure was in some cases. In between, there's a bit of a gray area in between 0.3 and 0.4, where you really need to look at the discrepancy and figure out what is the cause of it. To give you an idea of what this looks like, here are two pharmaceutical structures with very different levels of agreement between the PXRD and the DFT models. So for the sulfonation structure on the left, the PXRD model, the Rietveld refined model, agrees very well with the DFT structure. You can see you've got a very low RMS Cartesian displacement difference. These are basically identical structures for all intents and purposes. The RMS displacement is below 0.1 angstrom. They're very close. For the PXRD model on the right, for mupirocin, there's major discrepancies between the Rietveld refined and the DFT optimized model. The molecular packing is similar, but the detailed Rietveld structure is pretty clearly wrong here. And you can see how large the RMS difference is. So here's an example of a drug called donepezil. And this was one of the first drugs that was actually brought to market to treat mild to moderate Alzheimer's disease. I'm actually using lab PXRD data here again with a fairly low upper tooth theta limit of about 35 degrees. So again, this is high quality data, but there's not a lot of data content. The minimum despacing is at around 2.5 angstroms. So a lot of single crystal people would tell you, you can't solve a structure with that much data. So despite this minimal data content, I got a crystal structure that looked pretty chemically reasonable. But my first question should be, is it actually correct? And based on the DFT, the answer is yes. You can see the DFT structure here agrees very closely with the PXRD structure. We've got a very nice low RMS difference between the two structures. And even with this limited data set, we were actually able to solve this crystal structure. And this, again, was solved with parallel tempering with Fox. Yep.
So those two are very similar. Which one do you trust more?
At that point, the difference isn't enough to really make, like, they're similar enough. There's no main chemical feature that looks different particularly. You know, you've got the same geometries, and you know, there's slight discrepancies in bonds and positions. The hydrogens might not look quite as good because the hydrogens weren't refined with the PXRD. They were just placed around the molecule. So some of the hydrogens are off a little bit, but they don't actually go into that RMS difference calculation. So basically what I'd do is I'd say the refined structure is correct. To actually study the hydrogen bonding, use the DFT results. And that's sort of, this shows you what you can do. You know, again, the DFT, it's very useful for helping describe the hydrogen bonding, and it even helps you decide what you think constitutes a hydrogen bond. You can use the tools in the DFT like Mulliken overlap populations, which basically what they do is they calculate the amount of overlap or electron overlap between different atoms, and this can help you decide what constitutes a hydrogen bond versus what doesn't. All right, so here's a summary of some of the software I've mentioned. There's a lot of software on here. Most of this software is freeware, and I've focused predominantly on software I'm most familiar with. The exceptions to the freeware are at the very top and the very final steps. We had to pay for a license for Crystal, and you need to pay for licenses for the powder diffraction file and the Cambridge structural database. With Cambridge, it's very good to check your libraries. A lot of libraries will have a Cambridge structural database license, and you can basically download it and install it on your own computer. The powder diffraction file, not so much. But you'll have to find you can often find at your university people that do have a PDF license and may let you use it.
Jana is a paid software?
Jana? No, Jana's free. Yep. Expo is free as well. Yeah. They expect you to use it for academic usage. So hopefully I've convinced you that structure solution from powder data is a really useful tool. It certainly comes with its challenges, but for a lot of materials, it can be the only way you can get to a viable crystal structure. Much more so than single crystal XRD, structure solution from powder data really requires that you have significant knowledge of the molecular structure of your material ahead of time. You definitely have to use constraints and restraints to keep your structure solution and refinement chemically reasonable. And you really want to validate your structure if you can. And with another method, DFT is excellent for that, but there are other experimental ways as well. And I really need to thank a colleague of mine, Jim Kadek, who I've been very privileged to get to collaborate with a number of times. And I definitely owe him a great debt to his knowledge in this presentation in particular. And again, I've got a few different textbooks and sources of information that might be helpful to you. And are there any questions?
Thank you. Oh, you understood everything. Of course. How many softwares you have there? 20 plus, right?
Yeah, every problem is different. There's certain tools I've had the most success with, but there's different ways to approach and solve these structures. So yeah, and that is not an exhaustive list of software. There's a lot of packages out there and ways to go about it.
Does the specific determination in default work if there are multiple fields in the data set?
If there are multiple phases in the data set, resynthesize your sample. If you know what the other phase is, and particularly if it's minor, you can get away with going through the structure solution process, especially if you can identify the low angle peaks that are contributed by that second phase. There are limits though. And the higher a content you have, the more contamination you might get potentially of some of those intensities overlapping with the intensities you're interested in for solving the structure. So yeah, you've got to be very careful. In general, you want to start with the best sample you can.
So for inorganic structures, your DFT work even, or you have to use other different software?
DFT can work. Yeah. Yeah.
I'm thinking like organic molecule is more like isolated, right? So for inorganic, it's more like
Organic can tend to be simpler for using the DFT. You don't have to use as many reciprocal space points for your modeling. So it can be faster using organic structures, but you can do inorganic structures as well. Yep.
Any more questions?
So if someone is new to c.l.s, you showed lots of software packages. Can you, like which one, like c.l.s staff support to help new users?
GSS2.
Yeah, GSS2. You'll know. So if we go back a bit, go back to that. You'll notice for almost every step here, for the core steps, starting with ab initio indexing, all the way down to your structure solution, and you could add Rietveld refinement. I didn't even put Rietveld refinement, I don't think, as an individual. Oh, did I put Rietveld? Oh yeah, Lebail and Rietveld. Okay, yes. All these core steps, you'll notice GSS2 can do all of these things. So that's a great place to start. And Bob has awesome tutorials for not just the structure solution, but for various other steps, the Rietveld refinement and things like that. Yeah.
Any more questions? Well, you can find him later today and Thursday and Friday. So maybe we stop here. Thanks,
Okay.
Joel. And we're going to head upstairs to the third floor, room 367.